Good day. This is electrodynamics exercises, and we will do several exercises now. So I will start with one whose title is cylinder with a point charge inside. With a point charge inside. Okay, cylinder with a point charge inside. So we have a cylinder. I'm going to draw it. Okay, so as good as I can. Okay, and here the height of the cylinder is h. The radius is r. Okay, and in the center of this cylinder, we place a point charge. Okay, so I label the axis x-axis, y-axis, and this is supposed to be the z-axis. Okay, and here we have a charge of q. Okay, the discs which bound the cylinder and the side of the cylinder are all grounded. Okay, so we could say that phi, let's say we're going to take, of course, a cylindrical coordinate system to start with. Okay, and we can say that the cylinder, the boundary conditions are phi r theta h over 2 is equal to phi r theta minus h over 2 equals 0. Okay, so that's one boundary condition. Okay, and also another boundary condition is that phi radius theta z is also equal to 0. Okay, but there is a point charge at the center. Okay, so that's our problem. That's our problem. Okay, so now I will keep this sheet in mind. Sometimes I will remind the viewer of it. Okay, but I'm going to start solving the problem. Okay, first of all, if we look at this problem, the first thing that we notice is that there's no theta dependence. Okay, so as a result, we expect a potential function which depends on r and z only. Okay, and I can immediately write the Laplace equation in this case as partial phi r theta partial r squared plus 1 over r partial phi r theta partial r plus partial, so second derivative, r, sorry, apologies, this should have been a z, not a theta. This should have been a z. Okay, I'll fix that. Okay, so that's equal to 0. Okay, so that's actually the Laplace equation that we are after. Okay, so that's the Laplace equation that we are after. Okay, our first, the usual, so this is Laplace. Okay, and the usual ansatz is to take our z as a function of r only and a function of z only. Okay, so I take this usually ansatz, and then if I substitute, okay, so I'm going to have partial squared p r squared, that's multiplied by z, plus 1 over r. I've suppressed some notation, okay, so the arguments, okay, and there's again a z plus p and partial z squared. That all equals 0, and we're going to, of course, divide by the solution itself in the form in which we have taken it. So we're going to have 1 over p partial r squared, that's a second derivative, plus 1 over r 1 over p partial r. plus 1 over z, and that's equal to 0. Okay, so this is some basics. Okay, so, but now let us go back to the geometry. Okay, and let me actually explain the strategy that we will use to solve this problem. Okay, so let me actually try to draw this here. Okay, so that's the bisection plane, you could say, of the cylinder. Okay, and what we're going to do is write a potential for the upper half of the cylinder, so for z equals greater than 0, and a different one for z smaller than 0. Okay, so so given that, that's what we are going to do. Okay, but let me, okay, before actually I write the two different potentials, let us just notice one thing, is that we're going to first solve this. Okay, so first of all, we need a function z of z. Okay, we need a function, and well, we can immediately say what this function should be because we have one boundary condition. Okay, so now I'm going to work on this region, z greater than 0, and that boundary condition I can satisfy if I choose this function as hyperbolic sine, let's say kappa z minus h over 2. Okay, so let me first, for now, consider the upper half of the space. Okay, so I took this as my function. Okay, if I take this as my function for the remaining Laplace equation, is going to be an equation for p only, 1 over r, 1 over p, partial r, and this is kappa squared, and that's equal to 0. Okay, let me rewrite that slightly. So I'm going to let me write it as p prime prime. It's another kind of notation, 1 over r p prime plus kappa squared p equals 0. Yes. Okay. So now the next thing that we are going to do is to first, well, okay, we're going to make a variable transformation. Okay. And that variable transformation is going to be x equals kappa r. Okay, so if we make this variable transformation, then a derivative in r becomes d dx dr, in other words, kappa d dx. And similarly, you can easily show that the second derivative becomes kappa squared d squared dx squared. So my Laplace equation, or actually it's really just a second order differential equation, is going to look like, well, the first second derivative, so it becomes d squared p dx squared, sorry, kappa squared plus kappa squared over x dp dx plus kappa squared p equals 0. So the kappa squareds all cancel. Okay, and what we're going to be left with is d squared p dx squared plus 1 over x dp dx plus p is equal to 0. Okay, and we are after this one, and this one actually turns out to be the zero Bessel function. Okay, but let's work that out a little bit. Okay, so we have our equation here, and we can take p of x to be m equals 0 to infinity, and I'm going to take it to be a coefficient x alpha plus m. Okay, so that's going to be my ansatz to solve this equation. Okay, so let me actually state the first derivative is actually m equals 0 to infinity am alpha plus m x alpha plus m minus 1. We're going to need actually 1 over x p prime x, which is m equals 0 to infinity am alpha plus m x alpha plus m minus 2. And then we also need the second derivative to make everything complete. Okay, and that's am alpha plus m alpha plus m minus 1 x alpha plus m minus 2. Okay, so now let us just recall that this is what we're after. So, and I just worked out these two terms. I'm going to add these. Okay, I'm going to add those. So I actually get, so that's actually these last two terms. So I actually get m equals 0 to infinity. And if I add those two, I'm going to get alpha plus m squared am x alpha plus m minus 2. Okay, so this takes care of these two terms, this one plus this one, and I still have this one. Okay, but I'll bring it on the other side of the equation, and that's just the solution itself. So it's m equals 0 to infinity am x alpha plus m. Okay, so that's the power series that I want to actually start with. And the way, well, the first thing that we should note is here we have an x alpha plus m, here we have an x alpha plus m minus 2 term. So this series, where it begins, the very first term on this side will not have a matching term on this side. And the very first term, of course, is the m equals 0 term. Okay. And so basically, the first thing we can do to make everything function well is to set alpha equal 0. Okay, so if we set alpha equals 0, there will be no term on this side of the equation which does not have a matching term on this side. Okay, and having said that, then we can say that m equals 0 to infinity. I'm going to set alpha equal to 0, but I'm going to shift everything. So I'm going to have m plus 2 squared, am plus 2, x alpha plus m, and that's equal to minus m equals 0 to infinity, am x alpha plus m. Okay, now this is probably hard to read, but what I will do is use the recursion formula. Okay, and those three terms. So, I'm going to equate these term by term, and what I get from the term by term is am plus 2 is equal to minus am divided by m plus 2 squared. Okay, so now we have our recursion formula. I'm going to do one more thing with this recursion formula. I'm going to reindex it. This is a square. And the way I'm going to reindex it is I'm going to say m is 2j, okay, m equals to 2j, and I'm going to say this is j plus 1, and this is minus aj, and that's divided by, well, 2 squared j plus 1 squared. 2 squared j plus 1 squared. Okay, so basically, now we're in business. Okay, we can write our power series solution. Okay, and our power series solution is, well, based on this recursion relation, let's say a1 is minus a0 over 2 squared 1 times 1, and a2 is minus a1 over 2 squared again, 2 squared, okay, which is a0 divided by 2 to the 4th, 2 squared times 1 squared. Okay, so in general, you can write aj equals minus 1 to the power j, a0 divided by 2 to the 2j times j factorial squared. Okay, and that's actually and we can take a0 to be 1. Okay, and then we have actually sorry, this is a0, again, which we took to be 1. A0 is 1. So basically, we have our Bessel function. This is actually the recursion relation for the zeroth Bessel function. So basically, our let's say px, which is really the j0x Bessel function, is actually m equals 0 to infinity, minus 1 to the power j, minus 1 to the power j, x to the 2j, divided by 2 to the 2j and j factorial squared. Okay, so this is actually, I repeated this derivation, but really I will keep going, and I'm going to use the orthogonality relation that is valid for Bessel functions. Okay, so if I have a Bessel function, okay, well, first of all, this j0x Bessel function has zeros at n equals 1, 2, etc. Okay, so some we can determine these actually, but for now we just have to be aware of the fact that they exist. Okay, so it's an alternating series. This minus 1 makes this alternate. So these zeros exist. Okay, j0xn equals 0, and there's an infinite number of them because this is an infinite series. Okay. Moreover, I'm going to also use the orthogonality of Bessel functions, of the zeroth Bessel function in particular, which is, so basically what you can prove is that 0 to r, r dr j0 x m r over r, j0 x n r over r is, sorry, it's equal to r squared over 2 delta mn j1 xm squared. Okay, so we can, I didn't prove this, but this is the orthogonality relation for Bessel functions, and we are going to use this to solve our problem. Okay, so okay, now let us go back and look at what we have. Okay, so what we had, let me just remind ourselves, is we had a potential which depends on r and z, and we're going to somehow write this in terms of a Bessel function. Okay, but we have to make sure that the boundary conditions are satisfied. Okay, and the way to make sure that that happens is that a, we're going to say hyperbolic sine kappa x minus z over 2. Okay, but the other thing that we remember that kappa was actually kappa also appeared in the equation for p, right? So remember that our original equation for p looked like this, and kappa appeared here, and kappa was actually the scaling factor. So we had the relation x equals kr, okay, x equals kappa r, sorry. So basically this kappa is actually also the scaling factor which assures that your Bessel function is 0 at the bound at on the side of the side of the cylinder. So basically what you have to do is to say, I'm going to take j0 kappa r, but I'm going to take kappa to be xm divided by r. Okay, and then well, there's more than one zero for the Bessel function. Okay, so we have to sum over a whole sequence of terms like this. Okay, so basically our potential, and now I write the whole thing, is going to look like m 1 through infinity. I'm going to say am is a coefficient, and here I'm going to have j0 x m r divided by capital R, and hyperbolic sine. And sorry, I ran out of space, so I'll write the argument of this hyperbolic sine as xm divided by r z minus h over 2. Okay, so that's the argument of the hyperbolic sign. And this is for z greater than 0. Okay, and for the potential that lives below the xy plane, I can take another set of coefficients. I still take this Bessel function because this Bessel function assures me that I'm going to have a 0 on the side of the cylinder. And here I'm going to put xm over r z plus h over 2 because this assures that I'm going to have 0 on the bottom disk of the cylinder. Okay. Okay, so let me actually, fix this. I'm going to cross this out. It looks a little bit better. So this part is for z smaller than 0. Okay, and the first thing, of course, is to match the potentials to make them continuous. Okay, so I'm going to say phi r 0, and that's m equals 1 through infinity a m j0 x m r over r. Okay, and if I put this here, I'm going to have hyperbolic sign, but I made z0, so it's x m h over 2r, and there's going to be a minus sign there because that's a hyperbolic sign. And then for the bottom part, m equals 0. So this is really 0 plus. Okay, so I wrote here the limiting form of the potential as z approaches 0 from above. Okay, and here, sorry, that should have been a b. That's a b, pardon. That's bm j0 x m r over big R sine h x m h over 2r. Okay, and these have to be equal, from which we get that bm is minus am. Okay, so that's where we're at. So our potential right now looks like we eliminated one set of coefficients. So our potential now looks like phi r z is equal to minus m equals, sorry, not minus, m equals 1 through infinity. And here I'm going to have am j0 xm r over big R. And here I have my hyperbolic sign, xm over big R z minus h over 2. Okay, and that's for the upper half. And here I'm going to have m equals 1 through infinity minus am j0 xmr over big R hyperbolic sign xm over r z plus h over 2. Okay, so that's the potential. And our next task is to match these two potentials. So remember what we were doing. Here's my cylinder, and I have a charge in the middle. Okay, and the charge resides at the center of the cylinder. And this part is for the upper half, this part is for the lower half. And what I now have to do is match these two so that it's consistent with the fact that there's a charge at the center of the cylinder. Okay, and the way to do that is to actually really think of this whole plane as some charge density. Okay, so the charge density here depends on r. So I'm going to think of this as a surface charge density. Okay, so that's actually my surface charge density, and you know that the z component, or the normal across that surface of the electric field, okay, which might be a function of rho and theta, but it's not going to be a function of theta because we have ruled that out. But but the difference of these two, i.e., when I approach the xy plane from above minus approaching the xy plane from below. Sorry, this should have been an r, not a rho. Okay, that's the radius. Apologies for that. But so basically, this is equal to 4 pi sigma of r. So that's going to be our strategy. Okay. Now the next step that we have to do is to actually get these normal components of the electric field, which is of course obtained by taking the z derivative of the potential and multiplying it by negative 1. Okay. There's only one last thing that should be done before we go further, is to actually fix what sigma r is. Sigma r is a charge density, a surface charge density, about which what we know is that it's going to be proportional to this delta function, okay, because all the charge resides at the origin, okay? And we could say the following. What we know is that if I integrate from 0 to r, r d theta sigma r, okay, if I do that and I integrate it, I actually get the total charge. Okay, that's obvious. Okay, so from this, now the other thing is that sigma r doesn't depend on the angle theta. Okay, so we can actually integrate that out, and that just gives us a factor of 2 pi. So what we have is that q divided by 2 pi is equal to the integral of 0 to r dr sigma of r. Okay, so I have to rewrite this. It doesn't look very nice. Q divided by 2 pi is equal to the integral of 0 to r dr sigma r. But sigma r is actually proportional to this delta function. So so basically, that gives us that, well, the way that's going to work, of course, is if we take q over 2 pi delta r divided by r for this. Okay, so that's that's the idea. And based on this, we can immediately write that sigma r, okay, so sigma r is actually q divided by 2 pi delta r divided by r. Okay, so that's the charge density that we sought to determine, which is actually fixed by the fact that there's a charge residing at the origin. Okay, so that's that. Okay, and now I'm going to take the derivative of the potential with respect to z. Okay, so let me remind you, that's where the potential was written. Okay, so I'm going to take its derivative. Okay, so on the one hand, we are going to have m equals 1 through infinity, a m j0 x m r divided by capital R, and I'm going to have here an xm divided by r, and a hyperbolic cosine rather than a hyperbolic sine, xm over r z minus h over 2, and that's that. And then I'm also going to have another term, which is minus, so below the part that's below the xy axis, xy plane rather, j0 xmr over r, xm over r, hyperbolic cosine, xm over r, z plus h over 2. Okay, so that's where we're at now. And while I can multiply this by negative 1, And then what I have in each place is actually the electric field. So I can write that E Z component at Z, well, it's R dependent, so I'm going to write that, but it's 0 plus is actually minus M equals 1 through infinity AM J0 XMR over R xm over r. And what's this going to give us? That's just going to be a hyperbolic cosine of xm h over 2r. Okay, and then I'm also going to have ez r 0 minus, and that's m equals 1 through infinity am j0 xmr over r. Again, it's xm over r, hyperbolic cosine xmh over 2r. Okay, and now, so basically, if I subtract one from the other, I just get this one twice. Okay, so basically, what we have is that minus m equals 1 through infinity 2am j0 xmr over big R xm over r hyperbolic cosine xmh over 2r. That's equal to our charge density, okay, times 4 pi actually. So it's actually, it ends up being 2q delta of r divided by r, okay? Okay, and now our final task is to determine these coefficients. And those coefficients can be determined by taking a Bessel function with some arbitrary index, m, let's call it m prime. So I'm going to say 0 to r, r dr, j0, j0, xm prime r over r dot dot dot. So actually, and I'm going to use the orthogonality of the Bessel functions, which I've written in a previous slide. Okay, so if I apply this integral here, okay, so the only thing that depends on r is this Bessel function. So I'm going to get minus 2am. Here I'm going to have r squared over 2. That's going to be an m prime actually. J1 xm prime and this thing squared. And then I'm going to have here an xm prime divided by r and the hyperbolic cosine xm prime h divided by 2r. Okay, and then I have to do this to this side of the equation, the other side. And that's easy because this r cancels this r, okay, and all I'm going to be left with is 2qj00. Okay, so this gives a closed expression for am prime. This gives a closed expression for am prime. Okay, and that basically is the solution to this problem. Okay, thank you for your attention.